Okay, hi everybody. Thank you for attending today. Sorry about missing last week, but glad to be back. I know we're kind of low on attendance today because it's graduation and it's grading season. Yeah, I'm sure a lot of people will be watching this late, so we'll try to make this high quality for recording. I've already asked Nathan to ask as many questions as he feels like he needs to on behalf of everybody else. So hopefully that'll cover things. So last time, 2 weeks ago, we talked about regular functions on affine varieties and regular functions on varieties in general. And we said that a regular function was a function such that on some Zariski open covering of the variety, for each open subset, we could write the function as a quotient f over g, where g was not zero on that subset. And so now we're going to talk today about how regular functions relate varieties to each other. And so these are called morphisms of varieties or regular maps. And then we're just going to go through a bunch of examples of regular maps and then constructions of varieties. And then the thing that we'll try and end with, time permitting, is classifying the family of quadrics in projective n space. And this will be a lead into next lecture. We'll talk about next time this thing called elimination theory, and then these things called moduli spaces, which the family of quadrics in Pn will be an example of. So ignore the nice pictures for now. We'll get to that soon. Just to start, any questions or things that should be restated before we get into things, Nathan or Professor Webb?
No, I'll ask definitions when they come up.
Okay, and there's the notes that you can pull up too that should have most of the definitions. But if there's something that isn't in the notes, or if there's something that's maybe obscured in the notes, please feel free to ask. Okay, so yeah, regular maps. So we're going to define. First, we're going to define maps from arbitrary varieties to affine space. So we'll define this row from X to AN is called a regular map. If it is given by an n tuple of regular functions on X, basically sending points, x1 through xn to f1 of x1, f2 of x2, fn of xn. And then so a map between varieties is kind of a specification of this. So a map row from X to Y, where X and Y are in AN or affine varieties, is a regular map to affine space with the image of row contained in Y. And so this is kind of our notion of a map between varieties. And as always, we really want to know, well, what does an injection, a surjection, a bijection, and an isomorphism look like? Well, we like to say that because this whole business of maps between varieties is determined really by the fact that it's mapped to affine space and not just the second variety, we like to say that X is isomorphic to Y as a variety, if and only if there exist regular maps eta from X to Y and phi from y to x that are mutually inverse to each other. And then kind of an alternate way of saying this is if the coordinate rings, so the ring of regular functions, are isomorphic as K algebras. What we mean is just an algebra with coefficients in K, where K is the base field. And just reminder, so the coordinate ring is going to be the original ring mod I guess this would be polynomial ring that we're working with mod the ideal of the variety that we talked about last time. Okay. So maps to projective space, we keep in mind, so we defined all of this in terms of maps to affine space. Maps to projective space are a little bit more complicated, but they're obviously the thing that we're a little bit more concerned with because we've set up this whole business of projective space as the space where we like doing geometry, where it's easy and makes sense to do geometry. And so what we really need is that maps to projective space are regular if they're locally regular on each affine slice. So we talked about, we can view Pn by its affine covering, so I equals 0 to n of ui, where ui was the set of points x naught to xn such that xi is non-zero. We talked about how this was an affine slice. Well, if we view this as our affine slice, then we'll say that phi from a variety x to Pn is regular if and only if it's a regular map on each affine slice. And namely, the thing that this changes is that you can, and this is called the Proj construction. We'll talk about this in lecture, I think, 22. But the idea is that projective space is what's called, or it can be viewed as a graded algebra. And so the idea is that Pn should be this direct sum of affine spaces, not 1 to n, 0 to n. And so what we're going to really want is that if we have an isomorphism between two varieties, well, we can view x or y as, as some intersection of this graded algebra. And so then the idea is that, I don't know if n is actually the, no, n is the right thing. Basically, we want the coordinate ring, when viewed as a graded ring, to be isomorphic. And this is our idea of an isomorphism of projective varieties. So this is not super well written, but so this will be if and only if x is isomorphic as a projective variety to y. And then naturally this holds for quasi-projective varieties as well. Okay, so when we talked about regular maps to affine space, we said, okay, we can write all of them as this tuple of functions. this isn't true for projected maps. And actually our first example of a regular map will be a case where you can't just write a tuple of regular functions. And so yeah, essentially you have to have an n+1 tuple of homogeneous polynomials of the same degree, and not all zero. And this is to preserve our projected coordinate system. So just as an example, consider the curve in P2 cut out by x squared plus y squared minus z squared equals 0. When viewed on the affine slice 1, 0, 1, I think, or no, sorry, xy1. When viewed on the affine slice, xy1, this is a circle. I can't draw circle centered at the origin, I guess. Okay. And so our idea is that we kind of want to view a map from this circle to P1 as a stereographic projection from the point 0, 1, 1. And so the way this map will work, so we're going to send this to x and then z minus y. And so clearly this doesn't make sense at 0, 1, 1. Note, not defined. On 0, 1, 1. But if we have a point R lying on the circle, then phi of R maps to the line PR. And we'll call this point 0, 1, 1 P. And so again, kind of the way we're thinking of P is on our affine slice. This is P. But then we can extend the map to be a regular map by defining 5P is equal to 1, 0. Okay. So now let's verify that this is actually regular. So claim phi is a regular map. Okay. So what we'll do is we'll take coordinates s and t on P1 with our traditional affine opens. U0 is defined by the first coordinate as non-zero, and U1 is defined by the second coordinate being non-zero. Well, then taking the inverse image of each affine slice of P1, we get back the circle minus the point that this omits. So namely 0, -1, 1. And then of the second slice, we get 0, 1, 1. Now, on U1, this is pretty clearly regular. So if we pick our coordinate on U1 to be s over t, So U1 is t is non-zero. So we have, if nothing else, no divisions by 0. So in U1, we get the restriction of phi sends x, y, and z over to x over y minus z, which is s over t, right? And so then clearly this is regular on C minus 0, 1, 1, because that's where we would have a division by 0. But on the other hand, on U0, if we write our coordinate in terms of t over s, since s is non-zero, then we have phi inverse of u naught is equal to z minus y over x, which might not appear to be regular at 0, 1, 1, but we can do some algebraic tricks to make this work, right? So since again the whole point was to exclude this and then bring this over here, and then likewise here we're excluding 0 minus 1, 1. Okay, so then what we'll do, our little trick, will be multiplying by 1. And this gives us z squared minus y squared over x times y plus z. But then we said that x squared was z squared minus y squared somewhere in here. So we get an x squared in the numerator and x times y plus z. And so this is equal to x over y plus z. And so this is regular at 0, 1, 1, but is not regular at 0, negative 1, 1. Is regular at 0, 1, 1. Okay. So, yeah. So this means that we're regular at c minus 0, negative 1, 1. So this is a great case where the map from C to P1 cannot be given by a pair of homogeneous polynomials without common zeros. And so basically, if we're going to make a regular map to a projective variety or to projective space with a tuple of polynomials, they have to not all be simultaneously 0. So this is a regular map, though. It just takes a bit of work to define. Okay, so any questions from this example before we move on?
I think the fielding is making sense for this one.
Okay, cool. That's great. Okay, so let's get to some canonical examples. So we've already kind of talked about the Veronese map, but I wanted to revisit it because I don't feel like it was motivated the way I would hope it would be in the first lecture. So at this point, we've seen enough projective varieties to say that, if you're given some variety x cut out of Pn by a homogeneous polynomial of degree d, we can sometimes describe it in terms of finite or countable sets, but usually we can't. And especially as you add on equations and intersections of equations, this gets more and more difficult to do. But what we really want to do is we want to be able to view a projective variety in terms of like simple terms that are easy to understand the intersection theory of with other varieties. And so what we'll do is, since each term of the polynomial cutting out a variety has to be of the same degree, we can view it as embedded in a larger space that takes degree d monomials to be like linear terms, right? So the Veronese map V and D from Pn to P n plus D choose D minus 1 sends x naught to xn, maps over to basically power products of the xi of degree d. So what do I mean by power product? It's just a product of the xi's. So like x naught, x1 would be a power product of degree 2, or like x1 squared would be a power product of degree 2, or x naught, x3 cubed, x5 would be a power product of degree 5. And so kind of like as a base example of this, we can consider V2, 2. That's a good one. So here we're sending over x naught, x1, and x2 over to x naught squared, x1 squared, x2 squared, x naught x1, x naught x2, and x1, x2. And so if we have a variety, if x is in P2, is cut out by, let's just say, you know, f of, you know, x is equal to x naught squared plus 3 x naught x1 plus x2 squared. This is very nonlinear in P2, but over in P5, right? So in this case, this is P2 to P5. Over in P5, this is very much a linear term. And so this is just like a really nice tool. And in fact, like if you're trying to come up with nice intersections of things, you can often come up with transversal intersections in the target of the Veronese map, and then pull them back through the Veronese map to some lower dimensional space to embed it in like the projective plane, for example. So this is just like a really useful tool from an algebra geometric perspective. So it's kind of true. So this n plus d choose d minus 1 thing is not arbitrary. It's a fact, basically, that the number of monomials of degree d in n plus 1 variables is n plus d choose d. And so then we pick it to be n plus d choose d minus 1 because that's exactly how many things we'll need, because we add on the extra piece for projective space. Yeah. So another nice property of the Veronese variety. So okay, I guess here's another definition. So here I'm looking at the image of a Veronese map intersecting the image of a variety. Sorry, the image of a variety through the Veronese map. But we'll call the Veronese variety is just the image of V and D of Pn. And so, yeah. it's nice. How do I want to say this? So let's just call this V. When we talked about the rational normal curve, the rational normal curve is a special case of the Veronese map. We talked about it as the twisted cubic. The Veronese variety lies on a number of obvious quadratic surfaces. The rational normal curve is one of them. So this is a really clean way often to think about quadratic surfaces. Okay, other theorems about Veronese maps. So if we have, this is worth writing down. So if X in Pn is a projective variety, and if Y is the Veronese image over X in P choose N plus D choose D minus 1 is a projective variety, then X is isomorphic as a variety to Y. And so this is kind of clear from our example here. It's cut out by the same equation in both, but in P5 it's viewed as a linear subspace, and in P2 it's a very nonlinear subspace, but they are isomorphic. So this should give kind of some intuition about how varieties, relate to each other. Okay, and then kind of, this is the other thing. Any projective variety is isomorphic then to an intersection of a Veronese variety with a linear space. So if we have a Veronese variety in some space and we intersect it with the image of a smaller Veronese, then that's a linear space, and then we can pull back to get some isomorphism. Okay. So the next type of map is called a Segre map. So if you've seen tensor products of vectors before, this is very much related to that. So namely, given coordinates x naught to xn, and, or no, I guess I should do r and s. So x naught to xr, y to ys, in PR and in PS. Then the Segre map RS sends goes from PR across PS to P R plus 1 times S plus 1 minus 1 by sending pairs X and Y to X tensor Y, which is going to be the product of all of these. So it's this pair X and Y goes over to like X naught, Y naught, X naught, Y1, etc. X1, Y naught. It goes on. So it's all of the products of each of the terms. So namely, each coordinate is going to be a quadratic term. So monomials of degree 2. Okay, so what does this look like? Just as a picture thing, because I have a nice picture, this is a non-singular quadratic surface in P2. So at the end of this lecture, hopefully we'll have time to classify all of the quadratic surfaces in Pn. And this will be like our first legitimate algebra geometric result. But this is an example of a smooth quadratic surface in P2, namely of rank 2. And we'll talk about that later. Yeah. So it's characterized, namely, by at any point that we pick on the surface of this thing, it's the tangent space is going to be defined by two lines. So that's another way to think about the meaning of quadric surface is we want that to be true. As a computational example, consider the 1-1 Segre map, sending pairs x naught, x1, and y naught, y1 to x naught, y naught, x naught, y1, x1, y naught, and x1, y1. And what we'll do is we'll call this equivalently A, B, C, D in P3. Well, we can see that these coordinates actually end up satisfying that AC minus BD is equal to 0. And that if we view this as a determinantal variety, as the determinant of some matrix, this gives us the non-singular quadric surface in P3. So I showed you above the non-singular quadric in P2. This is just moving up a dimension. Okay. So the Segre map is really important because quadric surfaces are important, and they're interesting to study, and they're relatively easy to study. They're like a good grounding example of projective varieties. And so, of course, the Segre map is a regular map, and it's a really nice regular map. Yeah. Okay. So now we want to talk about a little bit of category theory that's going to just make life easier. So it's kind of an unfortunate fact that to do algebraic geometry, you have to be able to do at least a little bit of category theory. And so some people, like I really like that, but some people really hate that. I like to give just a little bit of an overview so that I can say some words and some colloquialisms, or bump proofs to, a commutative diagram. So this will be that. Okay, so it's kind of funny in the notes. I called this section just enough category theory to be mildly harmful. And this is a shout to Vakil's book. The first chapter is just enough category theory to be dangerous. We're not doing as much as he does, so mildly harmful. Okay. So what is a category? A category is a collection of objects and maps between objects. And they have to satisfy some things. So if the category is called C, then the objects are called obc. And the morphisms, or maps between objects, are called morc. So morphisms between objects. Now you can define this. I think there's like 11 axioms to define a category. It's worth noting that obc and morc technically don't have to be sets. There's this other thing called a class that they can be. So technically I'm defining what's called a small category. We're not ever going to talk about any like non-small categories in this class, so I don't think I need to get into that, but it's maybe worth noting that you can define this more rigorously than I am. The way you should think about category theory is you've seen categories for the whole duration of your math experience at JMU. Namely, like you've seen vector spaces, that's a category. You've seen groups, maybe you've seen rings, those are categories. If you've seen modules, which are like vector spaces with ring coefficients, category. Topologies and topological groups, categories. Sets are also categories. And then the morphisms between these objects are like kind of natural things that you know about. For groups, group homomorphisms are the morphisms. So a morphism is really like a function, but with some added property. So for example, so function plus some property. So like for example, a group homomorphism has for if phi is from A to B, where A and B are in group objects, then for all A and B in A, phi of AB is equal to phi of A, phi of B. So this is an example of like a morphism property that we require. Okay, so other stuff. So category theory is often used as like a bookkeeping tool for relationships between things that we care about, or as a way to pull out information about the morphisms between things. To keep track of this stuff and to make it neat to follow, we use things called commutative diagrams. And so the canonical thing you should be thinking of is in the category of groups, a commutative diagram could be seen as something like the first homomorphism theorem that we talked about in lecture 2. That G mod the kernel of the map to H is isomorphic to H, right? And so this is, and I guess this has to be surjection. Yeah. So this is like an example of a commutative diagram. And what it really means is that if you have something in G, if we call this map phi and we call this map, no, let's not use phi, let's use theta, and let's use eta. We should have that phi of G is equal to eta of theta of G. This is what it means to commute, is if you pour it like water, no matter which direction you take, if you get to an endpoint, it should not matter the path of morphisms that you take. This is what we mean by a diagram commutes or not. So the objects would be capital G, G mod the kernel, and H. And the morphisms would be theta and phi and eta. Generally speaking, we really kind of want morphisms to behave well with injectivity and surjectivity. Sometimes, for all of the categories that we care about, an injective map is sometimes called a monomorphism. A surjective map is sometimes called an epimorphism. There are categories where they don't mean the same thing, but we're working in a special type of category called an additive category. And usually actually in a subset of additive categories called abelian categories. And in those cases, monomorphisms are injections and epimorphisms are surjections and vice versa. So, okay. Given that we have injectivity and surjectivity and bijectivity working the same way that we want things to from functions, we kind of also want the notion of an isomorphism to carry over. But we actually do need to add on the same caveat that we did for morphisms of affine varieties, that we really, we need, for some map to be an isomorphism, we will always want there to exist a mutually inverse map that is also a bijective morphism in the category. So typically we'll say that it's like an arrow reverse, or no, we'll just call it an isomorphism. I'm jumping ahead. Yeah, but we always want like a mutually inverse map. So in this case, like from H to G mod cur H. But if there exists one, we'll sometimes write this little twiddle. Okay, so one of the more important things in general, just to be aware of, is the category of categories. So let's see. So the objects in the category of categories are going to be categories, right? So like groups, sets, rings, etc. And then the morphisms of categories are these things called functors. And so there are really two types of functors. We say that, so types of functors, there are covariant functors, which means that we preserve the direction of the arrows from one category to another. So, for example, if we have a functor f from a category C to a category D, if it's covariant, then for all G and H in ob C, and then phi from G to H in more C, we have the following commutative diagram. So from G to H by phi, when we say direction preserving, what we mean is that when we push down by f, we know we get f of G, we know we get f of H, but then what we also get is we get a map f of phi, and it's going the same direction. Naturally, I'm placing a big emphasis on this whole direction preserving thing because the other type of functor, called a contravariant functor, is direction reversing. So the idea is if we take the same commutative diagram, but we say, if f is contravariant, so if f from C to D is contravariant, then the only thing that's going to change is going to be the direction of the f of phi arrow, and it'll be going from f of H to f of G. So this is what we mean when we say co and contravariant. Okay, I think, oh yeah, okay, so the last thing I was going to say on this note is that we try to avoid saying that two diagrams or two categories are isomorphic. So if two categories have an arrow reversing bijective functor between them, then what that really means is that it's isomorphic in the category of categories. But we'll just say that two categories or two diagrams are functorial, right? So like in this case, the diagram from G to H is functorial to the diagram from f of G to f of H. If we were to identify it with its own name in this other category, D. So I don't know. That's just something to be aware of. Okay, so any questions about category theory before we get back to some algebraic geometry? I know that's a lot of information all at once.
You explained it really well.
Cool. All right. So you've seen a good example of a functor. Let me just say this before I move on. A good example of a functor. If you have a group, the group is built on a set. Both groups and sets are categories. So it stands to reason that if you have some collection of objects of groups and morphisms between those objects, that you can map all that over functorially to sets where you just forget the group structure and only remember the sets and the functions between sets without the homomorphism property. So like you've been working with functors every single time you've ever done group theory. You just kind of didn't know it. So anyway, that's probably like the most helpful example for knowing what a functor is. That's really for a covariant functor. I would have to think a little bit to get a contravariant example. I'm sure there's an easy one though. Okay, so products are kind of going to be our first application of this. You've seen the Cartesian product of sets, and that this is like a very natural construction. But one would maybe wonder, like, is this a universal thing? If I have two groups and I take the product of two groups, do I get a group? Well, we know the answer is yes, but the diagram for this is as follows. So given x and y and x product y, if we have some object z in our category with maps into both x and y, what we really want is that z should have to go through the product of x and y first. So as a general thing, we'll have pi 1, or really pi I, is projection onto the first factor. Meaning that it's just, you're dropping straight down from x product y to just x. And then this pi 2 would be projection onto the second factor. And so what we would, what we kind of have is that if, let's see, if phi is the map from z to x product y, and these maps are theta 1 and theta 2, that for any z in big Z, what we really have is that phi 1 of z is equal to pi 1 of phi of z, and that theta 2 of z is equal to pi 2 of phi of z, and that this is always true in any category. And we call this type of commutative diagram that's always true in any category a universal diagram. And so kind of our theorem here that we want to be like an obvious statement is that the product of two varieties is a variety. Okay, so this is kind of like we would want this to be true, and we would really like hate to have to prove this. Not because it's hard, but because it's like just so obvious. Let's try for something a little less obvious, or at the very least a little more interesting. So we'll define the fibered product over W as follows. So we'll take the same notion as some of the stuff from the product, but what we're going to add on, what we're going to add on is this extra object, W, and we're going to give x and y maps eta, and I'm going to color code this, eta 1 and eta 2 into W, and then the main change we're going to make here is we're going to add a symbol. And we're going to define the fibered product over W is all of the pairs in the product such that eta 1 of x is equal to eta 2 of y. And this is also a universal diagram. So the formal definition, set definition, is that this is all of the pairs in x and y such that eta 1 of x is equal to eta 2 of y, and that for any z with maps into x and y, it factors uniquely through the fibered product. And so then kind of our theorem is that the fibered product of two varieties through another variety of two varieties x comma y through a variety W is a variety. Now you're probably thinking, okay, this is like out there, this is kind of abstract. What's an example of this? It turns out that there is a very interesting and a highly useful example of this called the graph of a map. So if we let f from A to B, where A and B are varieties, we define the graph of f as capital gamma of f to be the set x and f of x such that x is in A, right? So this thing is the graph of f. And it turns out that later on, this is like highly used in algebraic geometry for a lot of reasons. But it's also just a tractable example that we can compute for any regular map between varieties. So our theorem is going to be that let x in Pn be any projective variety phi from x to Pm a regular map. Then the graph of phi, which is in x comma Pm, which is contained in Pn cross Pm, is a subvariety of Pn cross Pn. And then the proof of this is by fibered products. And so this is kind of an interesting case. So consider the fibered product through Pm of x. Well, just plugging in the universal diagram, we have projection onto the first factor, projection onto the second factor. And since we're fibering through Pm, we have this relationship where we have phi, the map that we care about, and then we have the identity map. Well, by the set definition of the fibered product, we know that this is the pairs x and y in x cross Pm, such that phi of x is equal to the identity of y is equal to y. But this is exactly the graph of phi. Well, by this theorem, that the fibered product of two varieties is a variety, since we know that Pm is kind of like a trivial variety, and since x is given to be a variety, then that means that the graph of phi is a variety. I think I said f, I meant phi. So, point being, fibered products are incredibly useful, and yeah, they're great, and we'll use them a lot because there are other contexts that they show up in. So we're right at 4 o'clock. There was a last section of this that I don't want to start because it's 4. And so what I think I'll do is I will start next time with the example that's section 3.3 in the notes. Because it's a good example for what's actually like the subject of next lecture. So next lecture we're talking about these things called moduli spaces. And essentially the goal of it is we want to classify all of the varieties or all of something of a certain type based off of some numerical invariant. So like for algebraic curves, we do this with genus, right? You have genus 0 curves of some degree, you have genus 1 curves of some degree, 2, etc. That's a moduli space. In the case of quadrics, what we'll see is that the rank of the quadratic form associated to a bilinear form, and I'll define all these things, the rank of that quadratic form in some space Pn defines the equivalence class up to continuous deformation of the quadric surface. And so, namely, we'll show this in P1, P2, and P3 concretely, but then we'll prove it generally. And so these types of problems are known as moduli problems. We'll also talk about projections from one variety to another as a method of elimination theory, which is a way of like making problems that are computationally difficult because they have too many variables into easier problems. So yeah, I'm excited for next lecture. Any questions before I stop the recording?
I don't have any, really.
Okay, cool. Well, I'll stop the recording.